Lesson 3 is all about the exponential function. This is a new type of function that we haven't seen before, which is also what the current unit is named after. Let's explore the properties of this new function in this lesson. This lesson will be broken up into two parts. Each part will be in the style of an investigation. In part 1, we're going to consider the exponential function f of x equals 2 to the exponent x. Notice, with exponential functions, the variable is the exponent. The base can be any number. I chose 2 in this example, but it easily could have been a 3 or a 4 or a 5. The rules still apply. Let's get started in part A. We're asked to complete the following table of values, then complete the first differences and something called the common ratios. The common ratio is new. Think of it like a first difference, but rather than subtracting y values, we divide them. So this would be a good time to pause the video, try to fill out the table on your own, and when you're ready, click play to resume. Okay, here we go. So we just substitute each of the x values into the function. So we'll start off with negative 5. We replace x with negative 5, so this evaluates to 2 to the exponent negative 5. Now if you punch this in on your calculator, you're going to get a decimal. I'm going to work with fractions and you'll see why later. Using your laws of exponents for negative powers, this can be written as 1 over 2 to the exponent of positive 5, which becomes 1 over 32. I'm going to write all of my y values as fractions like that. Carrying on then in this manner, your y value should be the following: 1 over 16, 1 over 8, 1 over 4, 1 over 2. Then 2 to the exponent 0 is 1, 2 to the exponent 1 is 2, 2 to the exponent 2 is 4, etc. We basically just keep multiplying by 2. So 8, 16, 32. Those are the y values that you should have got. Now for the first differences, we subtract consecutive y values. So for instance, the first difference would be 1 over 16 take away 1 over 32. This will work out to give you positive 1 over 32. I'm not going to show my work for the rest, but I'll write down what you should get. The next first difference should be 1 over 16, then 1 over 8, then 1 over 4, 1 over 2, 1, 2, 4, 8, and finally 16. I'd like you to notice something weird that happened. Notice that the first differences are basically just the y values repeating again. Take a look. Our first difference is 1 over 32, and we work our way up: 1 over 16, 1 over 8, 1 over 4. Essentially, the first differences are equivalent to multiplying each of the previous ones by 2, which is exactly the same thing that happens with the y values. This is the only function you've seen so far that exhibits this property. Now for the common ratios, we have to divide consecutive y values. So the first one would be 1 over 16 divided by 1 over 32. Instead of dividing by a fraction, we multiply by the reciprocal. So this becomes 1 over 16 times 32 over 1. And that simplifies to give you 2. Repeat this process by dividing consecutive y values. I won't show my work for every single one, but you should notice that they all evaluate to 2. First question, what do you notice about the first differences? The first differences appear to be a repetition of the y values. First of all, we can say they are not constant. And appear to be a repetition of the y values. Next question, what do you notice about the common ratios? They are all the same. Notice that the common ratios are equivalent to the base of the exponential function. All right, let's carry on. So now we're going to graph the points from the table of values. This would be a good time to pause the video, plot the points, the x's and the y's as coordinates, and then connect them with a curve of best fit. After you've plotted your points, click play to resume the lesson. Okay everyone, so you should have got a graph that looks something like this. I know plotting the points to the left of 0 were very difficult. I mean, we're dealing with very small decimal numbers, so you'll notice that all of my points appear to be scrunched over here, somewhere between 0 and 1. Don't worry about being too exact over there. We just want to get an idea of what the points are doing. So what I'll do now is connect the points with the curve of best fit, and it should look something like this. All right, put arrows at the end. And there you go, that's your exponential function. You can think of this as a new type of function similar to the 6 different ones we looked at back in Unit 2. Now we'll look at the properties of this function. First question, are there any values that you're not allowed to input into the function? In other words, do we have any restrictions? So let's write out the function f of x equals 2 to the exponent x. Remember, x is the input and f of x is the output. So what are you allowed to input into this function? The question I always like to ask you was, first off, are you allowed to input any positive number that you want? And hopefully, as you realize from the table of values, yes, all positive numbers are allowed. 2 to the exponent 1, 2 to the exponent 10, 2 to the exponent 20. Any positive number you want is allowed. What about 0? Are you allowed to input 0? Yes, you are, because 2 to the exponent 0 is 1. And what about negative numbers? As we saw, negative numbers are fine, because any negative number is just written because any negative exponent can just be written as a reciprocal of a positive exponent. So I hope that description was sufficient to convince you all positive numbers, all negative numbers, and 0 are allowed. Let me comment on this briefly. What this means is that there are no restrictions. And we're going to use this now to write the domain in part D. So as I just mentioned, if you're allowed to plug in any number that you want and there are no restrictions, then this tells us that our domain is equivalent to the set of real numbers. Part E now is going to involve us coming up with a range. First question, does this function ever attain a maximum value? And I'm asking you to explore by testing a few additional input values. We can actually see this from the graph though. If I just were to make a quick sketch of the exponential function, but I'd like you to look at the importance of this arrow. Notice the arrow keeps increasing up and to the right. This suggests that the exponential function will keep increasing forever and ever and never reach a maximum value. If you were to compare this, for example, with a parabola that opens downward, this parabola is never going to get higher than this point up here. We saw this last unit. So that would be the location of your maximum. However, the exponential function doesn't do that. So from the graph alone, we can see that no maximum is reached. Let's summarize. Okay, similar question in part F. Does this function ever attain a minimum value? So we can actually look at the graph and also test this out with some additional points. Look at the graph I drew in part E. You'll see as the function goes towards the left, it does decrease, but it never crosses the x-axis. Let's experiment with this. For instance, if you have 2 to the exponent negative 10, this is equivalent to 1 over 2 to the exponent of positive 10, which is 1 over 1024. What's 1 divided by 1024? I don't know, but it's going to be a really small decimal. In a similar way, 2 to the exponent of negative 15 is equivalent to 1 over 2 to the exponent of positive 15, which is 1 over 32,768. What is that number equal to? An even smaller decimal. So if you keep playing around with this, you'll notice that as the function moves to the left, the y values keep getting smaller, but they never get less than 0. So we can make a comment about this. The function never reaches a minimum value, but it does approach 0. And we'll use this information now to come up with the range of the function. So the range of our new exponential function is the set of y values that belong to real numbers such that y is greater than but not equal to 0. Take a look at the graph and verify for yourself that that is what's actually happening. Part H, what's the y-intercept of the function? Well, as we learned last unit, the y-intercept is always the y value that occurs when x is 0. So if you substitute 0 for x, we get a y value of 1, which is the y-intercept. That means the function crosses the y-axis at a y value of 1. Go back to the graph and make sure for yourself that the y-intercept is actually 1. Next up, what is or are the x-intercepts? Recall, this is the location or locations where the function crosses the x-axis. As we saw, it never crosses the x-axis. It never reaches a y value of 0. So this function has no x-intercepts. All right, a few descriptive type questions now. As the x values increase, what happens to the y values? We already answered this, but now we can generalize. So as the x values get bigger and bigger, or as x approaches infinity, you might remember in Unit 2, we used this notation when we were looking at the reciprocal function. So as x approaches infinity, y approaches infinity. In other words, as the x values get larger, the y values get larger. Part K, as the x values decrease, what happens to the y values? So once again, we already talked about this. As the x values get smaller and smaller, in other words, approach negative infinity, notice that the y values get closer to 0, but they never actually cross the x-axis. And the reason for this will be described in the next part. This is because we have an asymptote, specifically a horizontal asymptote. So I'll just make a quick sketch of the function again. Our exponential function looks like this. And because it will never cross the x-axis, that's going to be the location of a horizontal asymptote. There are no vertical asymptotes, so therefore we have a horizontal asymptote at y equals 0. Alright, and that completes part 1. Part 2 is very similar to part 1, but this one involves a slightly different exponential function. So first of all, it looks like this got cut off a little bit. That should be a 2. So now we're considering the exponential function f of x equals 1 over 2 to the exponent x. How's the function different from the previous one? Well, before we dealt with f of x equals 2 to the exponent x. So notice here that the base is just the reciprocal of the previous one. Okay everyone, very similar to what we did before, we're going to construct a table of values. So this would be a good time to pause the video, go ahead and complete it on your own, and when you're ready, click play to resume. Okay, first off, we have 1 over 2 to the exponent of -5. Using our power rules, we take the reciprocal of the base and the exponent becomes positive. So that's 2 to the exponent of +5, which is 32. Once again, I'm not going to show my work for every single one, but you should get y values of 16, 8, 4, 2, 1, a half, 1 over 4, 1 over 8, 1 over 16, and finally 1 over 32. In a similar way, complete the first differences by subtracting consecutive y values. So 16 take away 32 is -16. And work your way down the table, subtracting consecutive y values. You should get first differences of -8, -4, -2, -1, -1/2, -1 over 4, -1 over 8, -1/16, and finally -1 over 32. In a similar way, we complete our common ratios by dividing consecutive y values. So the first common ratio should be 16 over 32, which reduces to 1 over 2. In a similar way, you're going to find that all of your common ratios are a half. Alright, so we definitely see some similarities from the previous function in part 1, but also some differences. First of all, notice that the y values appear to just be in the opposite order. We start at 32, end up at 1 over 32, but in part 1 we started at 1 over 32 and ended up at 32. And the first differences also have a similar pattern, but now they're negative, whereas before they were positive. And the common ratios, once again, is just equivalent to the base of the exponential function. So let's make a few notes. Very similar to before, the first differences are not constant and appear to be a repetition of the y values. Okay, next up, what do you notice about the first product? Sorry, that should say first ratios. Once again, they are all constant and equivalent to the base of the function. At this point, you're going to graph the points from the table of values. Once again, pause the video and click play when you're ready to resume. Alright, so hopefully your graph looks something like this. As before, let's connect the points with a curve of best fit. Okay, don't forget to add the arrows at the end. Alright, the rest of this lesson follows a very similar procedure to previously. Once again, are there any values that you're not allowed to input into the function? The answer once again is no. There are no restrictions. As all positive numbers, negative numbers, and 0 is allowed. And you know what that means? If there are no restrictions, then your domain is the set of all real numbers. Alright, does this function ever attain a maximum value? So let's sketch the function here to help us in our response. This is the general shape of the exponential function in part 2. Notice now that the behavior seems to be the reverse of what we saw before. As this function goes up and to the left, the y values keep getting bigger and bigger. So once again, there is no maximum values. The y values approach infinity. Similar question, does this function ever attain a minimum value? So rather than plugging in some points, let's just look at the graph. Notice now that as the x values get larger and larger, the y values get smaller and smaller. As you may have guessed from before, the y values will never reach 0, but they certainly approach it. And as before, we'll combine this to write a statement about the range. The range of this exponential function is the set of y values that belong to real numbers such that y is greater than but not equal to 0. It's the exact same as the exponential function in part 1. All right, what's the y-intercept? So once again, we input 0 for x. that's 2 to the exponent of negative 0, which is just 2 to the exponent 0, which evaluates to 1. Therefore, as before, we have a y-intercept of 1. Recall the x-intercepts are the location or locations where the function crosses the x-axis. As we saw, this function never crosses the x-axis, so there are no x-intercepts. As the x values increase, what happens to the y values? So we can just look at the graph. As the x values get larger and larger or approach infinity, notice that the y values approach 0, but they don't actually get to 0. Part K, what happens to the y values as the x values decrease? As x gets smaller and smaller or approaches negative infinity, the y values get larger and larger or approach positive infinity. Notice that the behavior is the opposite of the function in part 1. Alright, there is a horizontal asymptote right over here, which happens to be the x-axis. So therefore, horizontal asymptote of y equals 0. And that wraps up the lesson. Let's summarize by looking at some properties of this new function. Alright everyone, so in this lesson or investigation, we looked at a new type of parent function, which is called the exponential function. And generally speaking, the parent function of this new type of function is f of x equals b to the exponent x. Here, b is the base of the function, x is the exponent, and in part 1 of the activity, we looked at an example where the base was a number larger than 1. In our example, that was 2. In the second part of the activity, we looked at an exponential function where the base was a half. In this case, the base was a number between 0 and 1. What I'd really like to stress here is that the base of the exponential function must always be a positive number. But there are two cases. It can either be a fraction between 0 and 1, or a number larger than 1. Depending on which of the two cases it is, we're going to have some similar properties. So let's look first of all at some common characteristics of both exponential functions. First off, they both have a domain, that is the set of real numbers. They both have a range, that is the set of real numbers where y is greater than, but not equal to 0. They both have horizontal asymptotes at y equals 0. They both have y-intercepts of 1. They both have no x-intercepts. And they both have constant common ratios. That's what they have in common. As for differences, when the base is greater than 0, that should say when the base is greater than 1. Please fix that. When the base was greater than 1, we noticed that the y values increased as the x values increased. In other words, as x approaches infinity, we saw that y approaches infinity. And in the second case, when the base is a number between 0 and 1, we saw the opposite, that the y values decreased as the x values increased. In other words, as x approaches infinity, y approaches 0. And there you go, that's the exponential function. Your homework for today is to complete the following extension questions. So answer these on the paper provided, and if you have any questions, don't hesitate to reach out. Take care everyone, and I'll see you in the next lesson.